Good morning, everyone. So I found we have a few in the previous class. So actually, I observed this trend during in many semesters. Actually, in the first or second day of the okay. So now this is the recorded. So actually, in the first or second day of the semester, there are many students in campus, but the number of students is decreased as the semester is going to the middle of the semester or the last day of the semester. So, but I hope every student sincerely participate in the lesson during the semester. Okay. So I will quickly review what we learned in the previous class. So actually, in the previous class, we learned about the overflow of the binary number arithmetic. So you need to just remember that the hardware system has limited resources. So which means that the number of bits. So actually, we can represent data or numbers using binary data or binary numbers, and then which means that is binary numbers have multiple bits, okay, multiple digits, but these digits are hardware resources. So which means that if we just decide the number of bits or number of digits of the number of digits in the binary data or binary number, then this number is fixed. So we cannot change the number of bits because this is the hardware. This is a hardware resource. So we cannot change during, if the hardware is fixed, then we cannot change. So which means that the number of digits of the binary data is also fixed. So when we perform the binary arithmetic, then we need to consider overflow or underflow. So actually, usually it is called overflow. So overflow means that the result of the binary arithmetic cannot be represented using the fixed number, the same number of the input output. So it cannot be represented using the fixed number of the result output. Okay, so this is the example. Actually, we need to use one bit for this RSB, the bit of the binary number. But if we just set the number of bits as 4 bits for the result, then we cannot represent this large number. This is called the overflow. And I also mentioned that the hardware system needs to detect overflows because overflow may generate errors in the system. Okay, it's very critical. Also, we learned about how to represent sign number. So I mentioned that the sign of a number can be represented using a binary digit because sign bit has only two values, plus and minus. So we can easily represent the sign of a number using a binary digit, a bit. And then I explained that there are two different methods. Actually, there are several methods that can represent the signed number system. But in the previous class, we learned two different methods that is used for representing the signed number system. The first one is the sign and magnitude numbers. Then the second one, use complement numbers. Okay. Then sign and magnitude number is similar to our real sign number system, real decimal number system. So it means that the LSB represents the sign, and then the remaining bits represent magnitude of a number. But I mentioned that we do not use sign and magnitude number system because why? Because we cannot apply normal arithmetic units for calculating sign and magnitude number system. This is the example. Okay, and also another reason is that there are two different representations of 0. Okay, we can represent 0 like 1 goes 0, and then 0, 0. And it's the same for the decimal number system, the real decimal number system. Because we use this sign and magnitude number system in our real number or our real numbers. So it is not a problem. But in a hardware system, you need to use the normal. You need to use the same hardware unit for calculating different numbers. So we do not use the sign and magnitude number system in the hardware. So we use COSE complement number system for signed numbers. So this is the definition of a COSE complement number system. So this is a definition. So which means you need to memorize the definition of this COSE complement number system. So in the COSE complement number system, the LSB represents the sign bit also. But the LSB also has magnitude, okay, the power of 2. So you need to remember that the LSB of the COSE complement number represents the -2 to the power of and -1. Okay, that's very important. And then we can add the magnitude of the remaining the same, but this is equal. The magnitude of the SB is A to the magnitude of remaining bits. Okay. The COSE complement number, and then also if we use the COSE complement number, then we can use normal, the same arithmetic unit for calculation. Okay, and then subtraction is same to the addition because same A minus B is A plus minus B. So which means that in order to perform subtraction, then we need to convert this number into the minus number, right? And we can provide the other unit. So so we can reverse the sign using this method. So you also need to memorize reversing the sign of the COSE complement number system. So first we need to invert the all bits of the number and then just add 1. Okay. And this is the example. So we using this method, and we can reverse the sign of the COSE complement number. And then we also learned about how to extend bit width of a COSE binary number. There are two methods also, the sign extension and the zero extension. So just to memorize, for the COSE complement number system, we need to apply sign extension. Sign extension means that when the bit number is increased, so bit width is expanded, then we need to just repeat the LSB. Then zero extension means that we need to apply zero extension for unsigned numbers. Okay, unsigned numbers just the plus number and 0. So for zero extension, we just add zeros on the left side of a number to increase the number of bits. Okay, those are what we learned in the previous class. Then please read the textbook. Then in the today's class, we learned about the logic gate finally. So we until now, we learned that the binary data, actually the digital systems handle binary data. Then we can represent binary data using binary number system. Okay, binary numbers are composed of multiple bits, actually multiple digits, and then bit represent the binary digit. So actually, in order to represent the binary number, we need to use many bits. Right. So in order to represent the 15 as a decimal number, then we need at least 4 bits, right? At least. So we can represent the 15 using the 8 bits, like the 00001111, right? So actually, because each digit of a binary number represents only 1 and 0, but in order to represent a very large number, like so I said that in a C program, integer includes the 32 bits. So in order to represent large number, we require multiple bits. So I said digital systems handle binary data. And I said that the binary data includes multiple bits. So actually, digital systems receive binary data, but this binary data includes many bits. So many bits are given to the digital system, and the digital system generate output. Okay, that is the typical operation of a digital system. Then we will learn about the logic gate. So what is the logic gate? So logic gate is a simple digital circuit. But this simple digital circuit receive one or multiple binary inputs and then generate the binary output. So when I explain about the digital system also receives binary data, multiple binary data, and it generates the binary output result. Actually, this figure is the same, which means that the logic gate also receives the one or multiple binary inputs and then generate binary output. Then what is the difference? So the logic gate is a simple. My writing is not good. So simple and then fundamental digital circuit that can compose complex digital system. So we can build. So this is the basic unit or basic circuit that can be used for building complex digital system. So if we want to build a digital system, then we can start from a logic gate. So this is the basic element that is used for building digital system. So logic gate receives the very simple binary data. Okay. So in this slide, you can find that it's simple digital circuit, right? And then this circuit just receives one or multiple. So which means that 1 or 2 or 3 or even 4. So but the number of inputs is So we just this logic gate just receive small number of input signals. Okay, and then generate output signal. Okay, that is the definition of logic gate. So actually, this is simple, right? So you can think that this is just a black box, and then we can. So it's just a module. So just to so I mentioned this the concept of modularity, right? Do you remember? Modularity. What is a modularity? So modularity means that it's a kind of what is the module, and then we can just define the input signals of this module and the output signals of the module. So we can define the function of the certain module. So that is the modularity, and then we can just organize multiple modules to yield a certain data system. So actually, this figure is very similar to this figure, right? So you can think that the logic gate is just a black box, and then this black box received several inputs, but 1, 4, 2, or 3 inputs, even 4, but several inputs, and then generate output. Then we can define function of this black box. Okay, we can understand a simple logic gate like this. Okay. So in this class, we learn about the several logic gates, like the logic gate performs logic functions. What is a logic function? Okay, so we learn about the inversion and or and NOR. So these are called logic functions. Okay, so logic function means that so actually this logic gate receives the binary data. So logic function means just if the binary data is handled and then binary output is generated, then this is called a logic function. Okay, then we can define the behavior of logic function. Okay, so we're done. And then we can classify logic gates based on the number of inputs. So these logic gates, not an buffer. So buffer means buffer. Receive single input. Okay, so which means that it's a black box, and then this black box receives only one input. Okay, and then these logic gates and or exclusive or something like that receive two inputs. Okay, you can imagine also the certain some logic gates can receive multiple inputs, like the 3 input and like 4 input 4. Okay. Okay. And let's learn about the NOT gate and POP gate. So if you learn about while you are learning about the logic gate, you first receive memorize the symbol. This is symbol. The symbol of logic gate, right? So we can represent the logic gate like a black box, but each logic gate has its own symbol. So we can usually use the symbol of a logic gate like this. Also, you need to memorize the representation equation. Okay, and then you need to memorize a function, the function of a logic gate. So I said that logic gate is defined as input and output. So actually this is simple. So in this figure, A is an input and Y is an output, right? So what is the same? So A is an input and then Y is an output. So then what is the NOT gate? NOT gate just inverts the input signal invert. Okay, inversion. Not gate. The function of the not gate is a inversion. So it just inverts the input signal. Then what is an inversion? What is an inversion? The 0 is changed to the 1, and then 1 is changed to the 0. So that is the inversion. And then we use bar to represent this NOT gate. Okay? So in a Boolean equation, so we use bar here to represent the NOT gate, and then this is the symbol of the NOT gate. Then this is the input, and this is an output of the NOT gate. And what is this value? If input is 0, it's very simple, right? It's 1, and then it's 0. Okay? And then pop. Pop is just the input is the same to the output. So which means that the input signal is just delivered to the output of this pop gate. So actually we can write y equal a for representing pop gate, and then it's same. So actually the input is just delivered to the output. Then why do we need to pop? The output is the same to the input value, right? And why we need to run pop? So actually, I will explain about this digital subroutine in this class. But actually, I said that the real hardware, the real world, actually a hardware system or hardware circuit handle analog signal. Okay. So actually, which means the analog signal may include noise signals. So in order to clarify the input these signals, electric signals, we can use okay. So this is the hardware logic. So we can insert verb to clarify these electric signals. Okay. So just remember that the signal of the pulse is the triangle, and then the input is just delivered to the output. Then, so this is the number. And then you can find this small circle in front of output of not gate, output of not gate, right? So what is equal? So if we use output gate, then there is no small circle here, but we can find a small circle here. So usually, this logic design, this small circle is called a bubble, and then bubble represents inversion. Okay. We can find many bubbles in the digital logic gate. Okay, so just to memorize that bubble, if we just add bubble the digital logic gate, then it represents inversion. Right. So if we just see the buffer here, then we cannot find any bubble. So A is just delivered to the 1. But in the NOT gate, we can find a small bubble here, which means that this signal is inverted. Okay? So if you find a bubble, which means this represents inversion of a signal. Okay? Just remember that. And again. So these are two input logic gates. The AND gate has two input bits, A and B. Also, the OR gate has two input bits. So this is a symbol of an AND gate. Then this is a symbol of a logic gate. So actually, the difference is this one and this one. Okay. So AND gate and OR gate receives two inputs, the two input logic gate, and then generate one bit output signal. And then we can represent AND gate as the multiply, like A multiply B. So sometimes we can use multiply sign for representing AND gate. But usually so actually we can represent multiply like this, so we can represent AND gate like A multiply B. And then we can, Boolean logic, the OR gate is represented using adder sign. So this is not a real add operation, but you can use this plus sign for representing OR gate. Okay? So multiply the Boolean equation, multiply actually is used for representing AND gate, and then this plus sign, and sign is used for representing OR gate. Then I said that you need to memorize the definition. So this table is called a truth table. Okay. So in a truth table, we just list the all available input bit signal. Okay. So in this figure, we can find that in the AND logic gate has two inputs. So we have two inputs here, and then this is a bit. Okay, a single bit. So which means that each bit can have two different values, 0 and 1, right? So and then because there are two inputs, there are four different pieces of A and B, right? So the 0, 0, 0, 1, 1, 0, 1, 1. Then we can define the output of Y based on these different input values. Okay. Then what is the definition of AND? So definition of AND is that if O which are 1, then output Y becomes 1. This is a definition of AND operation, not this the logic design, this the logic. Okay, it's so that or if all bits are 1, then Y becomes 1. So by definition, we can figure out the output value of AND gate. So this is it's too easy, right? This is 0 because there's no 1. And then this is 0, 0, 1. Okay? So as you can see, all inputs A equal 1, and B equal 1, Y becomes 1. That is the definition of AND gate. As you can see, the property of AND gate is similar to the property of multiplication. That's why we use multiplication for representing AND gate. Okay? Then, what is the definition of OR gate? Or so one of input for 1 and output becomes 1. This is the definition of OR gate. So by definition, we can figure out the output of OR gate is 0, 1, 1, 1 because we can find 1 here. So the property of OR gate is similar to AND operation, even though the 1 plus 1 or 1, 0, but you can say that this is not an not zero. So that's why we use add operator to represent OR gate. But just remember that this add operator is different from real add operation. Okay? So this is OR gate. Okay. And then there are different kind of two input logic gate. So let's think about the exclusive OR. So the exclusive OR is represented as XOR. So it's an exclusive OR. It's called an exclusive OR. So exclusive OR has also two inputs. And then the symbol of exclusive OR is like this. And then we use this operator for representing exclusive OR. And what is the definition of exclusive OR? So we learned about the definition of AND gate. We learned about the definition of OR gate. And then what is the definition of exclusive OR? The definition is exclusive OR means that if two inputs are different each other, then Y becomes 1. This is the definition of exclusive OR. So exclusive OR. So in the exclusive OR, we can just compare the two inputs A and B, and then if the values of A and B are different each other, then output becomes 1. Okay? This is the definition of exclusive OR. So then what is this one? It's 0 because it's the same. The values are the same. So Y becomes 0. And then O. For this one, O. So A and B are different each other. So it's 1, 1, and then 0. So that is the definition. So because this is the definition, so we need to memorize. Then we can find NAND gate. So actually NAND gate represents the not plus AND. Okay? So that's why we have AND here. And then if you see the symbol of NAND gate, you can find bubble here. So then I already explained that the meaning of a bubble. What is this bubble? Bubble represents inversion, right? So then what is the definition of NAND gate? So it's very simple, right? So bubble is located in the output of AND gate. So which means that NAND gate just inverts the output of AND gate. Okay? So I already mentioned that NAND means the not plus AND. So which means that the output of AND gate is just inverted. Okay? And then as you can see, you can use bar here because bar means also inversion. Okay, so this A multiply B represents AND operation, and then AND operation is inverted. So that represents the NAND gate. So what is this one? 0 NAND 0 equal. What is this output? It's 1, right? Because actually n 0 and 0 is 0, and then it is inverted, so it becomes 1. So it's a simple. This is 1, and this is 1, and this is 0, right? And then if you see the NOR gate, oh, the same. We can find bubble here. Okay, so OR operation is inverted with the NOR gate. So this is 1, 0, 0, 0. And then this is called the exclusive NOR. So exclusive. So exclusive, which is exclusive and NOR. So this is the inversion of exclusive OR gate. So we can find the bar here, and we can find exclusive OR symbol here. Then what is the output? Output is the inversion of exclusive OR gate. So it's simple, right? 1, 0, 0, 1. Okay. So actually, so these are basic logic gate. So actually logic gate. So we can find several logic gate, like the inversion, the invert, and then AND gate and OR gate and exclusive OR gate. So actually, if you just memorize the definition of a NAT gate, that gate is just simple. So AND gate and OR gate and exclusive OR gate, and that's fine. So actually, NAND means the NAT plus AND, OR means the NAT plus OR, and then exclusive NOR means the NAT plus exclusive OR. So if we just memorize the definition of AND, OR, and exclusive OR, then we can just know the output of NAND, NOR, and exclusive NOR. Okay? So these are basic logic gates. That's it. It's very simple, right? It's easy. Okay? Like we can find the bubble here, which means it's not. So we can also consider multi-input logic gate, like the NOR 3. So how can we define the output of NOR 3? So if you see the Boolean equation here, we can find that it's A or B or C, and can find inversion, the bar. Then how can we, then bar is just inversion. So which means that we need to define A or B or C. Then how can we define 3 input or? And actually it's simple. So I said that the property of OR gate is similar to the property of add operation. Okay? So which means we can, so it's very low level. So we can actually rewrite this equation like A plus B and plus C, right? Right. We can not perform A plus B plus C, then we can just first perform A plus B and then plus B. We can perform plus C. Okay? Then it's the same. In the OR gate, the 3 input, this is the 3 in OR gate. So in order to perform the 3 input OR gate, then we can just perform like A plus B first and C. So which means that we can generate the output of the A or B first, and then with the result of the A or B, we can also perform the result or C. Okay? Then what is the output of this Y? Because this is the NOR. So actually we can first generate the output of 3 input OR. 3 input OR. So output is it's a 0, right? It's a 0, 0, 0. And then how about this one? This is 0. And then 0 or 1 is 1 actually. Right. And then with the same way, it's 1, 1, 1, 1, 1, 1. Right? So actually by definition, so I also explained about the definition of OR gate. Definition is that one of inputs have 1, then output becomes 1. That is the definition of OR. And then if the number of input is larger than 2, right? Then this definition can be also applied. So which means for the OR tree, if the one of inputs have 1, then output becomes 1. But this is the lower tree. So output is inverted, so output becomes the 1, 0, 0, 0, 0. Okay, it's easy, right? Even though the logic can have more than 2 inputs, but we can apply the same definition to the multi-input logic gate. Okay? And how about the 3-input AND? It's the same. We can think like A, B multiplied by C, like the multiplication. But we can also apply the definition of AND gate. What is the definition? Definition is that all input are 1 and output becomes 1. This is the definition of AND gate. Also, this definition can be applied to multi-input AND gate. So it's 0, 0, 0, 1. Right, because all inputs are 1 and our output becomes 1. So we can define the multi-input AND gate. Okay. So that's why I mentioned that we can just memorize the definition of AND or exclusive OR. So 2-input AND gate, 2-input OR gate, and 2-input exclusive OR, also including not is the example, right? So that is just a model, inversion of the bit. So if we just memorize these 3 2-input logic gates, then we can apply the definition of these simple logic gates to the NAND gate, NOR gate, or exclusive NOR gate. Also, we can apply the same definition to the multi-input logic gate. Okay? It's very simple, right? Okay. So and then that's it. We learn all basic logic gates. Okay. Then it's just simple and it's easy. I think it's easy, but these simple logic gates are used for doing very complex data system. Okay. Yeah, it's a very good question. So he asked about the multi-input exclusive OR. So it's the same. So the symbol of the exclusive OR is symbol, right? So multi-input exclusive OR, we can write the multi-input exclusive OR like this: A exclusive OR, B exclusive OR, C. And then like the normal mathematics, we can apply. We can rewrite this equation like this. So firstly, we perform exclusive OR for the first 2 inputs, and then we perform exclusive OR for the result of the exclusive OR and C. Then how can we write the how can we figure out the output of 3-input exclusive OR? Okay, I will use this truth table. Do not. So just delete this one. Then how can we calculate the three input exclusive OR. So you
can just perform the first two. So it is 0, 0, 1, 1, 1, 1, 0, 0.
Right? And then
So
this
this
is
is
the
the
result
result
of
of
the two input exclusive OR. And we
you
can
can
just
just perform the exclusive OR to the tip
for
to this one. So
as you can see,
this is the 0, 0 and then 0, 1. So while output becomes the 0 and then 1. It's 1 and 0. 1, 0, 0, 1.
Okay. This is the output of two input exclusive OR. Okay. So and then as I mentioned, we can perform multi-input exclusive OR like this. The first one. So by definition, we can just perform the two-input exclusive OR. The first two input signal and then perform the exclusive OR. With the result of this OR and then that's it. But how about the 10 input exclusive OR? So we can just apply the same method to the 10 input exclusive OR. But as you can see, multi-input exclusive OR is just the hard pair. What does that mean? Actually, exclusive OR just count the number of ones. So for example,
we have 10 inputs. Oops. So 10 input exclusive OR. Where is it? So exclusive OR 10.
So this means that this exclusive OR receives 10 bits. So output means that we just count the number of ones for the multiple inputs, and then if this count is odd number, then
Output becomes 1.
And then if the number of ones is an even number,
output becomes 0.
So that is also, so we can easily actually calculate the multi-input exclusive OR like this. Do you understand? Okay. So if exclusive OR has the multiple inputs, then we can just count the number of ones, and then if the number is an odd number, then output of multi-input exclusive OR becomes 1. But if not, then output becomes 0. So that's why multi-input exclusive OR is called an odd parity. So it just detects the odd numbers of odd counts of ones. So
we can apply this property here. It's a 3 input exclusive OR.
So
0, 0, 0.
The number of ones is 0. This is an odd number, even number.
So this output becomes
0. And then
0, 0, 1.
It's 1. It's an
odd number. So it becomes 1. How about the 1, 1, 1? There are
3 ones. Becomes 1.
1, 1, 0.
The count of 1 is 2. It's an even number. So it becomes
0.
So this is the property of multi-input exclusive OR. Okay, we can apply this property like this, but actually if we know the property of exclusive OR, then we can easily figure out the multi-input of exclusive OR. Okay, good question. Okay. This is the end of the Bayesian logic theory. As I mentioned, we can just memorize AND gate, definition of AND gate, OR gate, and exclusive OR gate. And that's it. And then based on this knowledge, and we can yield the Boolean equation, and then Boolean equation is used for building complex digital logic. Okay, but the basic logic gate is very simple. So we can build from is simple logic gate. Then now I will explain about the logic level. So it's a real world problem. So I mentioned that the real world, all signals are analog signals like this. Analog signals means that the signals have many levels, many different values, and then these signals are continuously connected. So continuously, so we can observe that the analog signals are the levels of analog signals are continuous. But this is the example of the digital signal, or we can find the discrete levels of digital signal. So, and then I also mentioned that not to use, not to apply digital systems. So actually, the analog signals need to be converted into digital signals. So how can we convert this analog signal? So I mentioned that we just set the threshold level. This is the threshold. And then a certain value is higher than the threshold level. Then we can define, oh, this is 1, and this is 0, and then 1 and 0. It's very simple. So which means that we can represent this analog signal as this digital signal. So during this period, the value of this signal is 1. And during this period, the value of this signal is 0. It's simple, but there is a critical problem in this concept. Why? There is a critical issue, a critical problem in this concept. Because of noise. Actually, this figure shows a very clean analog signal without noise. So we can just think, oh, this is this signal, oh, this is 1, and this is 0, and 1, and 0. But in real world, noise signal is included in the real signal, real data. So when the noise signal is included, so it's added, then we can observe the real signal like this. Okay, so noise is added. So if noise level is too large, then we cannot figure out the real signal. But usually, the noise signal is smaller than the real signal. So then what is the problem? Actually, there is no problem in this reason. Okay? We can just think that, oh, this is 1. But if we just see this region, and this region, and this region, and this region, the problem is that the signal is fluctuate near the threshold level. So which means actually, if the noise is added to the real analog signal, and then at this region, the digital value becomes like this one. Oops. 0, 1, 0, 1. Also in this region, 0, 1, 0, 1, 0, 1, 0, 1, like this. Because if we just compare the real this analog signal with the threshold level, and in this region, the 그래서 this signal can be lowered in threshold for a short time, and then it will change frequently. So
Actually, this is the ideal signal you want to use. But if we just apply this concept, it's a very simple concept, then is the signal changes frequently at this region.
and that's the problem. So we need to simplify. We need to simplify. In order to use the logic, we need to simplify the real analog signal. But
You can find very frequent changes of these levels
at this point, okay, we need to avoid this problem actually. Okay. So actually,
If we just consider the signal, then I mentioned that the signal has only
two values, 1 and 0. And then
and usually one represents the ground, and which means the
0 volt, 0 volt DC, and then
one
1
represents EDD or
it's a high voltage. So when we build a digital circuit, then
actually you can build a digital circuit like this. It's EDD and it's ground, and then this is the input, this is output.
actually
The output signal
swings
between
0
0 volt to the
VDD
here, like this.
Okay, that is the real circuit, real digital circuit. The output swings between 0 to VDD. And then we assume that
Oh, 0 is ground, and then 1 is VDD. If
this signal is VDD, then this is 1. And then it's 0, this is 0. Or it's ground, and this is 0. That's our convention. Then how about
but we know that
analog signal, in the real signal, the analog signal has many different levels. How about the
VDD minus 0.1 volt.
like 4.9 volt? So if the VDD is
5 volt. And then if the level is the 4.9, the VDD minus 0.1 volt,
then how can we
represent this value to the
digital signal? And how
about
about
the 3.2 volt,
how about the
2.5 volt. So half of VDD. So we can apply the very simple concept like this. Oh, if so, this is the VDD, and then this is the ground, 0 volt, and then and then we can set the threshold as half of
VDD.
and then if this value is higher than the half of VDD, and it's 1, and it's lower than half of VDD, and it's 0.
We can apply the simple concept like this, but I already explained that if we apply
This simple concept
to the real world, and because of noise, then we can get the
very
dirty signal. So it's not clean. The output is the signal becomes dirty. Okay? It's not clean. So we cannot
apply
this concept. So
actually in the real digital hardware, so we apply some
complex, the complicated conversion to the digital circuit. So, so then let's think about the noise. So what is the noise? So anything that
degrades the real signal is called
noise. Okay, and then actually in the real world, noise means annoying sound. But in the real circuit or real system, the noise means that any signal that creates the real signal. Okay, is called a noise. So which means that noise is toward our real signal, so distort the signals. And then actually there are many there are many components that cause noise. Okay? So for example, the resistance, power supply noise, coupling wires, something like that. But this is the kind of electric circuit knowledge. So I believe it's hard to understand. So which means that the signals. So you can just remember that, just memorize that the signals can be distorted, changed by noise. Okay, and then we need to consider this issue in the real world. Okay, so this is the example. So what is this symbol? It's buffer. And then also you can find a buffer here. And then also let us assume that the VDE is 5 volt. So, and then this is the digital circuit, and I also mentioned that in the digital circuit, the output swings between 0 to VDD. So which means that the output signal has the 0 to 5 volt value. And then we can actually this is the digital circuit. So digital circuit usually generate the signals like the 0 is the ground, and then 1 equal VDD. So this is the 5 volt. So let us assume that this driver, this digital circuit generates the 5 volt signal. It's a VDD. Okay. So which means 1. But because of noise, like the resistance of this wire, also the interference between other components, is a kind of electric circuit issue. Then this level can be changed. So in this example, let us assume that this voltage level becomes the 4.5 volt. The problem is that, as you know, this is a buffer. So which means that, if 1 is given and 1 is generated, and then 0 is given, and then 0 becomes output of the buffer. And then we set 1 equals 5 volt. The VDD, but this buffer received 4.5 volt. So what happened? So actually this value is different. So we assume that actually this driver generates the 5 volt signal. Which means the result of this driver is 1. And then this is the wire, electric wire. And then so 5 volts is delivered to here is wire. But because of resistance and then other interference, then the voltage level is changed to 4.5. How can we decide this input? So this concept is called the logic level. So actually, we learned about the logic gate in the today's class. We think that logic gates are very, very simple, right? So 1 equals 1 and 0 equals 0, and then 1 plus 1 equals 1. Like that. It's very simple, right? It's kind of
elementary arithmetic. So, 1학년 되면 arithmetic. So, but in the real world, in the reality, the circuit, the circuit is the real world is more complex. We need to consider this real issue. And how about the 4.5 volt? So we think that 5 volt is the one, but how about this one? We don't know. So we need to decide how to convert this level into the digital value, like binary data. Okay, we need to decide the conversion rule. Okay, and then actually you can find the buffer here. Okay, so I said that if we use the buffer, then the input is just delivered to the output. So like 1 is 1 and then 0 is 1. Then you may think that, oh, why do we need buffer? Because of this issue. The signal can be changed by noise signal. Like so signal strength is reduced and then buffer change this value into the real 5 volt value. Okay? That's why we need buffer in the real hardware. Okay? So in a digital concept, 1 is 1 and 0 is 0. So we may think that, oh, this value is not changing. The wire is just connected. But in a real signal, the analog signal is changing because of noise. That's why we need to reproduce the output signal using a buffer. Okay? Why we learned about the buffer. Okay? So let's see the real waveform of the voltage value. So as you can see, if you see the PDF file, you can find that this is the actually rectangular waveform, actually ideally. But as you can see in the real world, this level fluctuates. Okay, so you can find that this fluctuates like this and fluctuates like this. So this is the real problem. Okay. So we need to decide the conversion rule more realistic conversion rule. Like so usually we can think that you can decide you can set the threshold level at the half of the VDD, but it doesn't work in the real world. So we need to set the real conversion rule in the circuit like this. So this figure shows the conversion rule of the output of the digital logic and then input of the digital logic. So actually, when we design a digital circuit, then we need to set the output constraint, the output characteristics, and input constraints of voltage level. Okay, so this is called the constraint. So constraint means that when we design a digital circuit, then output value is as the levels within this range in order to work properly. Okay? So let's see what is output constraint and then output characteristics. So this is the driver. So driver is the logic gate, and then logic gate will generate output signal Y. Okay, and then if Y, the output signal is generated, then the voltage level should be in this range if the
output logic level is 1. And then if the output value is 0, then the real analog signal should be in this range. Okay? So as you can see, this is the VDD, and then this is the ground. And then this range is defined as so it's a low output range. So it's the output value is 0. And then if the output is 0, then the voltage level should be within this range from ground to the VOL. Okay? Output low level. And if the output value represent 1 in the signal, then this output voltage level has the range between should be range between VOH to VDD. Okay? So which means that this circuit works within, need to work within these ranges when the output is generated. And then this is the input constraint. So even though output is generated within this constraint, like this range, because of the noise, so this voltage level can be changed. So this is the receiver. So actually the output of this circuit becomes the input of this circuit, right? It's the purple. So when the signal is delivered to this input of this receiver, then the signal can be distorted, changed. So this is the allowed input range, which means that if the input value has the value between this VIH to VDD, so VIH to VDD, then this input logic gate think that, oh, this value is 1. And then if this input voltage level is within ground to VIL, then this input logic, this logic gate think that, oh, this input is 1. Okay? This is the input constraint of this circuit. And then you can observe that this range is larger than the output range. Why? Because of noise. So noise will be included in this wire, the circuit wire, and so the value can be changed. So we need to set this input range is larger than the output range of the wire. And then this difference is called the noise margin. So noise margin, this is the definition of noise margin. So noise margin means that amount of noise that could be added to the worst case of output. So noise margin guarantees that the noise is added. So the voltage level can be changed from this output value. But the input value can think that, oh, this value is 1 if the value is within this range, and then this is the allowable noise to this output signal. That is called the noise margin. Okay, which means that if the circuit is tolerable, tolerable, this amount of noise. Okay, you understand? So actually, the real world problem is more complex than this type concept. But when we design the circuit, the real circuit, then we need to consider this noise signals to create margin. So we need to design the is the circuit like this. So actually this is the definition of noise margin of OH minus IH and then L minus OL. Okay, so this is my margin. Okay, so okay. So we can stop here. Then please read the textbook, and then in the next class I will also cover the remaining part of the slide. Then I will explain about the real design. Any question? Thank you for attention. See you in the next class. I'm done.